So this is going to be a quick one today. It's chapter 10.4 in the mechanics book, and it's just a slight addition to 10.3, which was where we introduced F equals to MA, and that was on Monday's lesson. So there's really only one example to show you, so it's this is hopefully going to be under 6 or 7 minutes. So in chapter 8 we saw that many physical quantities could have both direction and magnitude, so therefore we could represent it as a vector. A couple of examples of those were velocity, acceleration, we looked at mainly, displacement, that's distance but also taking into account direction, and then also force. Force can be applied in a direction. So these can be represented as a vector as well, because we could have a force that goes slightly up and right. You could be pushing at a diagonal. We would need a vector to represent that. Same goes for the displacement, acceleration and velocity. And things that are scalars. Scalars are things that cannot act in certain directions. They are just a number. And we have things like mass, area and volume. Because a mass is a mass. It doesn't matter if you flip it on its side. It doesn't go in a direction. It just is a mass. Gravity is what makes it go in a direction, which is the acceleration. So it's the acceleration that's the vector part. Mass is just still the scalar. And this naturally means that F equals ma works with vectors too, because we have a vector here for force, a scalar for mass, and a vector here for acceleration. And hopefully you remember, when we multiply a scalar by a vector, this is an example here, it just turns into a vector. So this side is going to turn into a vector, the left side is already a vector, so we have a vector equals a vector. We can then start to solve some problems with that. If we just had a number equals a vector, we would have problems. That's not solvable. So we just use our F equals ma, but in the context of vectors. So let's have a look at this question below. So let I represent east and let j represent north. That's what they do anyway. I is the unit vector that goes like this, and j is the unit vector that goes like that. A resultant force of 3I plus 8j newtons acts upon a particle of 0.5 kilograms. Find the acceleration in vector form. So our resultant force is our F. So where it says F, let's put 3,8. I am going to translate it into this column vector, then afterwards I'll turn it back. I think it's easier to work in this column vector method in this case. The mass is 0.5, so I'll just put 0.5 there. And then the acceleration is, well, P and Q. I'm using P and Q because that's what they've put in their solution, or in the form they want it in. So I'll use that. So I'm just going to times both sides by 2 to get rid of this 0.5. So that's going to give me 6 and 16 equals to P Q. So therefore P equals to 6 and Q equals to 16. If we solved it in the IJ form, so I'll do an alternate solution for this, seeing as I don't have too many examples to go through, we could also solve it as 3I plus 8j equals to 0.5 brackets pi plus qj. And then when we times by 2 again, we have 6I plus 16j equals to pi plus qj. And then when we get to this stage, when we're using in i's and j's, we want to equate coefficients, so only the I movements will equate to the I movements. So if I look at my i's, I have 6 equals to p, and if I look at my j's, I've got 16j equals to qj, so therefore 16 equals to q. There's no possible movement in the I that's ever going to affect the j on the other side of the equation, so only j links to j and I links to I. So you can do it both ways. We get the same answer. It's completely up to you what your preference is. It's good to be comfortable doing both ways though. And then we need to find the magnitude and the bearing of the acceleration of the particle. So of the acceleration, so we're going to be using the vector we've just found. The acceleration equals to 6i plus 16j meters per second to the minus 2. Let's do a quick drawing of that. So we start here, let's go 6 across, and let's go 16 up. So it's going to be a bit steeper, and it's going to look like this. And we can draw the triangle out, 6 and 16. So the magnitude is nice and simple. The magnitude is where we do Pythagoras. So we're going to do 6 squared plus 16 squared, and we're going to square root it. And that tells me that it is 17.08 blah 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 blah. However they want us to round it to, it doesn't say. We haven't used gravity at all in this case, so we're not restricted to rounding it to 2 significant figures. Maybe I'd say 17.1 though, for 3 significant figures. And then when we go to find the bearing, remember there's 3 rules for bearings. You measure from north, you go clockwise, and your answer needs to have 3 digits, no decimals. So let's draw the north line in. What we're actually concerned about for the bearing is this. Bearing of the acceleration, so from north to the line that our acceleration draws. But what I'm actually going to do is I'm going to use trigonometry to find what theta is here. So theta equals to tan to the minus 1 of opposite over adjacent. Which equals to 69.44. So therefore, alpha, which is what I'm actually after, equals to 90 subtract what I've got here. I feel like we've done these types of questions with magnitude and acceleration, magnitude and bearings and angles of vectors in 4 different chapters now. So hopefully that was kind of just teaching you how to suck eggs almost. You may want to round that to 20.6 for 3 significant figures, but it doesn't specify what it wants us to do. So here's a question for you to have a go at. So pause the video, replay it once you've had a go. Okay, hopefully you've had a go, and let's have a look at my solution. Well, first of all, we want to find the resultant force, and that's by adding these 3 vectors together. When we do it, we simplify it down to 5 plus 10p I and 150 plus 20q j. We then use F equals to ma. They should be underlined or bold, them vectors there. So my resultant force equals to the mass, 60, times by the acceleration. I can then just times this side, so 60 times 0.8 is 48, 60 times minus 1.5 is 90. We therefore know that the I component equals to the I component, so 5 plus 10p equals 48. We can find p is 4.3 from solving that equation. And then we know that the j component is equal to the j component, so 150 plus 20q equals to minus 90. And we get q is minus 12 from solving that simple equation. And that's it. I'll post a list of questions for you to have a go at, and that is between pages 167 and 169 in your textbook. Thank you.